This is tutorial number 6 in the playlist that I'm preparing for modal analysis of shear frames, shear frame structures. Now, uh, in this particular problem, I will be using the beam elements to model the frame, and I will create a tie connection between nodes that have different node numbers, but they are physically at the same location in order to make sure that everything moves in unison. Uh, these tutorials are intended for people who are thinking about transitioning from the Abaqus CAE program to the 3D Experience platform, whose native FEA solver is actually the Abaqus package. What I do is I select problems which are done in their entirety by some other YouTubers in the YouTube, and they're available, and replicate the steps in the 3D Experiences interface to highlight the differences and the similarities between the two uh, platforms. The particular problem that I'm going to be doing is a three-story building. In reality, this is three-dimensional. However, if the frames are evenly spaced, uniformly spaced, one can approximate that three-dimensional structure with basically a two-dimensional problem with multi degrees of freedom. Now, it is coming from the reference below, where this problem is done in the Abacus CAE, but that reference, its two-dimensional treatment, which I'm doing here, actually starts at 12 minutes into the video presentation. Okay, so there's some information here about the size of the type of the element that I'm going to be using and the size of the element when it comes to modeling it as a two-dimensional problem. Now, the dimensions are given there, and it's assumed that the material is steel, as you can see here. But because we're going to be using this thing as a lumped model, lumped parameter system, what we're going to do, we're going to reduce the stiffness or the density of the steel dramatically by a factor of 10,000, and instead use the dimensions and this density in order to come up with the values M1, M2, and M3. But when it comes to the structure itself, these beam elements, the density is dramatically reduced. The shape of the cross section is a box like this with these dimensions, and based on these dimensions and the dimension of the structure as a whole, these lumped values can be found out to be 5181. This is all calculated in the YouTube reference that I gave. Basically, it's taking the volume and multiply by the density, true density, and then come up with that number. Uh, it looks like this problem originally came from the CRC book, Structural Dynamics by Eswani. All right, so we'll get to that later on. I'll come to these slides later on. Okay, so when it comes to creating tie connection, which I've done several times in the tutorials, maybe uh, 2 through 5, we have gone through these few times, and you'll see it as we go along doing it. Okay, so let me go here. The units are already set to the things that I want. So I'm going to create basically 9 points. The 9 points are 1, 2, 3, 4, 5, 6, 7, 8. Actually, 8 points. Okay, and then these lines. Okay, and I'm not going to join these lines because I want you to be able to use the connection, the tie connection. But in tutorial 1, I actually joined them so that you don't have to worry about the business of tie connection, etc. Actually, tutorial 1 and 2, in tutorial 1, I joined them. In tutorial 2, I made sure that when it's meshed, duplicate nodes are merged together, but not here. Okay, so let's start creating our points. Here the point. Oops. Let's start with the 0, 0, 0. Let's go one floor up. So that is 3 meters up. So Z is 3. Let me bring it closer so that we can see it. The next one is 6. The next one is 9. And repeat these things. The only difference is that the Y is going to be 3. So that's going to be 3. This is going to be 6. These are all meter. And this is going to be 3. And finally 0. Okay. Now I will also create one more point. That point is going to be used for orientation point because the shape of the cross section is not circular. So what I will do is I will make this thing as x of maybe 3. So there is the orientation point. And okay, and then cancel. So we have 8 points like that, and this is the 9th point that is used for orientation purposes. Okay, so now we now create the lines going from this point to that point and going from here to here. This is left column on the 3rd floor. These are the right columns. The order that you pick these things don't matter. I would have done a lot less work if I actually created these as a sketch and then joined them, but that kind of defeats the purpose of the tutorial, but I'm going to use tie connection. And right there. Move this thing out of the way. Good. And done. So this is the frame structure, 3-story frame structure. Now let's apply material properties to this. So we're going to go and go to tools, create a material, and I'm going to call this thing steel, 3-story or frame, steel frame. And this is February 12, 2024. Okay. Once the template is created, then I'm going to apply it right there. So I'm going to say apply. I'm going to close these. I'm going to apply it to that. Green check mark, and we're going to input the value. So we go here, double click on it. Structural density, that's the reduced density by a factor of 10,000. So 0.785. If you try to make 0 of that thing so that it's not counted, it'll come back with an error message. Okay. Apparently in Abaqus you may be able to do that, but not here. So Abaqus, now we go to Abaqus Multiphysics, Mechanical, Elasticity, Elastic, and that is 210 GPa. That's Young's modulus for steel, and Poisson ratio is 0.3. So that takes care of the material. And that's pretty much it. So let's do a quick save here. Now we're going to go to mesh this thing. And one way to do that, you can go to from the top left corner using the compass, go to structural model creation, empty FEM. Okay. And now we're going to go and mesh this thing. These are beam elements. Click on that. We have to do this thing as many times as we have lines here. If I had joined it, it would have been all in one shot, but we're not going to do that. And the size, because I want, global size 50 millimeters, 50 mm. In fact, I have it here in my first line. It says global side 50 millimeter, and the type is this. This is the parabolic element, though it doesn't make that much of a difference, but yeah, so mesh, and then repeat this thing for these other guys. So let's do that, and I have to do that separately because of the way it's being done. Mesh, okay. These numbers don't change. Let's do the vertical column. Right vertical column. And now the beams, starting from the top. And that fellow. Oh, good. All right, now there will be duplicate nodes at these junctures because of the way we have done this thing. Okay, so now we're going to do the section properties. So we go to properties, first the profile. So under beam section, this pull-out menu, we have the beam profile, and we're going to go with a box, and the size of the box is basically given down here. All right, so let's do that. This is going to be box 250. Height is 250. Oops, sorry, 300. That's what I meant, 300. This is 300. And the thicknesses are 25 each. 25, 25, 25. Well, these should be millimeters though. Millimeter, millimeter, millimeter. That would have been a disaster. Millimeter, 25 mm, and 25 mm. Okay, so we created the profile. Now we're going to do, here's the profile. And now we're going to do the beam section. So patiently, we're going to do the same thing here. Now remember, the horizontal ones are also going to be, the section is going to be applied to it. However, these are going to be later declared as rigid. And if they're rigid, although we put a section there, it really doesn't matter. So let's start with the, and I think you can, because I think you can do all of them at the same time. Yeah, so let's do that with the control. Yeah, not the control, just select. You can do that. With meshing, you could not, but with properties, you can. And the profile is going to be profile that we created, profile 1, and the orientation point is going to be that. And we say, okay. All right, incidentally, if you want to see these cross section, you click on the display, and on the display preferences, you can go and say, show me the solid, and there they are. But I don't want to do that, I just say none, and good. Okay, so that takes care of these things. Now we're going to declare these to be rigid. The question is how. So under the connection, there is the rigid connection. You click on it, and patiently you have to do that. So this support is rigid. For this support is rigid, and for the support tool, namely the reference point, you right click, create a support, create a point, select that edge, and it says where I want it. For example, you can put it on that curve, or you can put the coordinates, whatever you want. So I'll put it on that curve, ratio halfway, exactly halfway, 0.5. And then you say, and then, the curve is right there, right? And then we say, okay. So a point has been created, and this point should be selected for that particular reference point. In fact, that point will be the point that is created here, point 11. Okay, that's fine. We say, and notice that here I'm going to make kinematic. This is very important, kinematic coupling. Say okay, and repeat this thing for the other guys. So let's do another one patiently. So you have to select this. Once again, right click, create a support, create a point, select that. Yeah, select this. Yeah. And yeah, halfway. So we say okay. And for the support, select that point for the reference point. This vertex is selected. Again, kinematics. Let's do another one. This beam. Right click, create support, create point. Select this point that's already selected. Okay. And halfway, right there. And for that point, for that reference point, we select this point. Agree. That's me. Kinematic. Good. This somehow that doesn't look right. This looks too far. Oh yeah. So let me go to this. I'm not sure why that point is not quite where I want it to be. Let me see for a second. Oh, 0.5. That's what I wanted. Somehow it ended up with 0.6. Okay, very good. Now, uh, let's update this thing. Or actually, we can, where are we now? Let's go back. Oh, the reason I went to the part design is because I selected that point. Let's go back to the finite element. Okay, good. Now, what we want to do here, update. Let's update these things. Yep. Now, what you want to do is you want to make put a mass lump mass here. So under the abstractions, here's a lump mass. We're going to put one over there, and the value of it is based on the slide 5181 kilogram. 5181 kilogram. And repeat this thing for the other ones. That same location, same reference point, 5181. And one last one, 5181. Okay. Now we created a rigid the duplicate node at these sides. So what you want to do is make sure that the node here is tied to that rigid element. So that brings us to these slides. So we go to the tie option, okay, and we'll see. So let's go to tie one, tie option. So under the connections, there is a tie. You click on it. So the main part of the structure is that starting from the bottom is that floor. Main or primary, and the secondary one are these 4, 2, 3, 4, because the duplicate, they're actually at this location of 3 nodes, so we want to tie them together. Now, we will come back. You'll see that this is going to cause a problem. We will come back and change this number because with this thing, it will not run. But for now, we just ignore it. We'll come back to this later on. And then repeat it for the other ones, except for the top one. There's only 2 secondary ones that you have to take. So this is okay. This is Taiwan, and again, this is the second floor. And for the secondary, we select these lines, and yeah, we'll come back to that again. It's going to be type 2. You can see that these are actually created here as you go along. You can see that. Type 2. Last one is going to be for the top floor. So the primary is the floor itself. And for the secondary, it's these 2 lines. We say, okay, we'll come back. Okay, good. So that takes care of this. And I'm pretty sure we're okay here. Let's do a quick save. except that it will not run. We're going to come back to that later. All right, so let's go and go to the structure of scenario creation. We use our mesh right there, finite element model. Let's do a quick update here. Oh yeah, missing step. Okay, no problem. So because notice that the step is missing right here. So there's no procedure. So we go to procedure and we're doing a dynamic frequency step. 10 frequencies to be extracted. That's okay. Everything stays the way they are. And now we can update and now it's going to be okay. All right, let's go and apply our restraint. We're going to solve this thing as a two-dimensional problem. That means we assume that all of these lines or these elements stay in the YZ plane. So first of all, as far as the boundary condition goes, we're going to go to fixed displacement. We're going to select all of them and say that you guys cannot move in the direction X. Yeah, you cannot move in direction X, and because it's two-dimensional, in principle, we should say rotation about Y and rotation about Z also equal to 0. If you left these out, it's probably okay, but all right. Now, well, actually, if you leave it out, it can actually twist, go on the torsional condition. We don't want that. So you should prevent those rotation. Now, these bottoms are clamped, so let me hide this point because I want to make sure that I don't inadvertently put a restraint on these points here. I can put it on vertex, but not on the point. So again, fixed displacement, you select this point, and because it's clamped, all of them are 0. I mean, basically these two rotation and this already comes from what we just did, and we do 2 of them. Both of these are clamped. So we go, let's do a quick save. All right, no loads here. This is a frequency calculation or natural frequency calculation. There are no loads. So now we're going to go run it. First thing, we're going to go to simulate. Let's do a quick model check. No problem. Now we do a simulation check. And let's see what happens. While this is running, let me see. We will go back. You see that we will get an error message, and we will go back, and you have to basically check this and put a number, and we're going to use 20. Now, problem right here, you can see that the problem is that the documentation is not very precise on the nature of this thing that we're doing, because these are really intended for surfaces, but we have to apply to wireframes too. So, and this kind of a thing came up in tutorials 3, 4, and 5. This one is 6. So we say fine. Now, how you come up across that? If you look at the diagnostic file, it's making a reference to that point that I mentioned. So let me close that. So we're going to go we go back to those entities. The entities were over here. You can see that. It was under tie, I believe. Yeah, you check that. We got 20 millimeters. Same thing with the other one. 20 millimeters. 20 mm. And we say, okay. Let's do a quick update. No problem. We're going to go back to scenario. We're back in scenario. And let's do a simulation check now. You click on it. What we have done here, working all the tutorials that we have done 1 through 5, there will be an issue here, as you will see in a minute. So you see, we run into a problem, and when you read this message, it says something about kinematic coupling. That being the case, what I'm going to do is change that kinematic coupling to one of the other two available and run it again. So I'm going to close that, go back to this rigid connection. Instead of kinematic, I'll use continuum distributing. Say okay, same thing here. Same thing there. And now we're going to run it. And that issue is going to go away. Now remember, there was a checkbox that we checked, and we put a 20 millimeter that if you take those things away, even with this continuum distributing, you will see that it bombs out. So it has nothing to do with that checkbox. That checkbox has to be checked, and a particular tolerance should be put in there, but kinematic does not work. You can see that. Now, these are the values that I get, and unfortunately, these values do not match this thing that is presented in YouTube. So there's something different between the work done in the YouTube using Abaqus CAE and what I've done here, and I can't figure out what the issue is. Just to convince you that if we go there and take these if we go to the tie and take these checkboxes away, something that worked just now is not going to work. So these are two independent things that have to be considered. So let me try to run it. It's going to bomb out again and produces the same message that I got initially when I did the kinematics coupling. It's going to bomb out. Yeah. Very good. So that's the end of this tutorial. Now in tutorial 7, I will repeat the same problem, except that we will not use beam element, we'll use solid elements completely to create that frame structure, 3-story frame.